Welcome to this technical explainer. Today, we're diving deep into the marine structural engineering that makes heavy offshore lifting possible. Specifically, we're going to analyze the structural adequacy of the MT-6012 vessel's hull design, right where it meets the MacGregor cargo crane pedestal. We'll be looking at the massive 100-ton crane, finite element method data, DNV stress tests, and strict operational parameters. If you're designing or operating offshore structures, you're absolutely going to want to stick around for this one. All right, let's look at our roadmap. We'll quickly run through the crane's key specs, move into our FEM model, break down 8 boom loading scenarios, evaluate our allowable stress limits, and then tie that structural engineering right back into actual operation modes. Section 1. Let's establish the parameters of the MacGregor crane and the key specs of the HMC 3586 LKO system. We're looking at a system with a max lift capacity of 100 tons at a 15-meter radius, and it can push 25 tons out to an extended 32-meter radius. The whole shebang rotates on a slew ring over 3.5 meters in diameter, with an estimated total weight of 256 tons. These numbers really highlight the massive, highly dynamic loads that are constantly being transferred right into the pedestal. What's really fascinating here is the view from the cabin. From up here, operators manage these colossal loads while having to constantly account for critical vessel stability constraints, including a maximum combined list and trim of 5+2 degrees. It's a high-stakes balancing act. Now, absolutely crucial to these offshore operations is the active heave compensation, or AHC system. This tech relies on a motion reference unit tucked inside the crane's pedestal control cabinet. It calculates the vessel's vertical pitch and roll movements and dynamically compensates for them in real time. This is what keeps subsea loads completely steady relative to the seabed, no matter what the ocean is doing. Section 2. Let's look at our finite element method modeling and how we idealize the MT-6012 hull structure. To get an accurate picture without melting our computers, we use a dual mesh approach. Notice the contrast here. We've got a general, relatively coarse 300 by 300 millimeter mesh for the wider hull structure. But we drill down to a highly refined mesh right at the crane pedestal, keeping those element dimensions strictly under 100 by 100 millimeters. For the structural engineers tuning in, here is exactly how we modeled the foundation stiffness. We used 4 and 3 node shell elements for the plating and web plates to perfectly capture membrane and plate bending effects. On top of that, beam elements with eccentricity were applied for the flanges of longitudinals and stiffeners. This combo gives us a highly accurate model of both bending and axial stiffness. Section 3. Setting the model boundary conditions to prevent rigid body motion. This image beautifully illustrates our coordinate system and exactly where the forces hit. The crane loads are applied as a rigid region right at the slew bearing level, exactly 17.6 meters above the base plane. You can clearly trace the direction vectors for the horizontal, vertical, and overturning moments. The make or break detail for our boundary conditions is how we prevent rigid body motion. We locked the model down completely by fixing all nodes in the planes of frame 26, frame 53, and the centerline plane across all degrees of freedom. This setup perfectly mimics the interaction with the adjacent, unmodeled ship hull structure. Moving to Section 4, let's get into the 8 boom loading scenarios and really stress test this foundation. To prove the integrity of the deck reinforcements, we couldn't just test one position. We simulated 8 specific load scenarios, from LC1 through LC8, rotating the boom in 45-degree increments. This full 360-degree sweep is absolutely vital for uncovering any hidden structural vulnerabilities in the transverse or longitudinal framing. Check out this table to grasp the sheer scale of these forces, which include a dynamic amplification factor of 2. Look closely at LC1 and LC2. We're applying a massive downward vertical force of negative 6,500 kilonewtons, alongside a staggering overturning moment of 44,000 kilonewton meters. These are absolute worst-case design loads. Section 5. Evaluating allowable stress limits by comparing our results directly to DNV standards. We benchmarked our results straight against DNV rules for ships. For transverse members outside concentration regions, the allowable normal stress is capped at 223 megapascals, and the allowable von Mises equivalent stress is 250 megapascals. These are the absolute structural yield boundaries we are working within.
Zooming in on this pedestal cross-section from our ANSYS output, we've pinpointed the specific stress concentration zones. You can see them marked here as L1 at the top of the pedestal and L2 near the internal structural connections. This is exactly where the geometric stiffness changes and forces naturally bunch up.
And here is the major takeaway for the engineering team. The analysis confirms structural adequacy. Now, yes, under load condition 1, equivalent stresses do marginally exceed the yield limit right where the sideshell plate meets the pedestal. But, and this is the key point, those exceedances are limited to a maximum of 2 finite elements, and the stress drops off incredibly fast in the surrounding elements. Because it's a highly localized peak, the structure is deemed fully adequate under DNV rules.
Section 6. Operation modes and maintenance, or how we safeguard the crane's life cycle.
For the operator in the chair, engaging advanced subsea modes like auto tension requires a very strict sequence. First, the running system has to be disabled via the armrest key switch. Only then can you select the mode on the screen. Pressing confirm kicks off the background valve preparation, and finally, the operator physically activates the mode using an acknowledge foot switch. This multi-step process ensures those massive forces we just talked about are applied smoothly.
To maintain the structural integrity we just verified, the preventative maintenance timeline is rigorous. Every 3 months, or 500 hours, crews must inspect the hydraulics for leaks, vibration, and abnormal noise. Annually, emergency functions are tested and checked for corrosion. And every 5 years, major components require a complete overhaul by authorized technicians. Which brings us to a final, crucial point. The manual strictly states that using third-party parts completely voids the MacGregor warranty. But I'll leave you with this question to ponder. Beyond just losing your warranty, how exactly does using unverified, non-genuine parts threaten the hard-earned structural safety margins we just proved with our FEM analysis? Throwing an unknown part into this system isn't just a paperwork issue. It's a fundamental structural risk to the entire vessel. Something to really think about the next time you're reviewing a maintenance log. Thanks for tuning in to this explainer.